All right, welcome back. So today I want to talk about some LP formulations, all right, or forms, and you'll be seeing this many times throughout the rest of the class. Different forms, all right. Some are useful for other reasons, and it becomes important to be able to switch between the forms. Okay. For example, when you learn the simplex method, you're going to want to put your problem, depending on whatever form it is, and you want to get it into a specific kind of form if it's not already in it. All right. So we'll do that. We're not going to do that in this specific short lecture, but in the next one we'll go ahead and manipulate between forms. All right. So today I just want to introduce, or this lecture I just want to introduce these few forms, so you have an idea when you see them what form it is. Okay? So today we'll talk about the standard form. We'll talk about another form, which is the inequality form. And then actually some books might have they switch between, sometimes they call another standard form the standard form. So I'll actually show you two forms. They do share one piece that I'll highlight, and then I'll show you a general form. Okay, so let's go ahead and start with the standard form, the first version of the standard form. So, well, first of all, of course, it's a linear programming problem. So you have a linear constraint. All right, so that's common for all of the forms. All right. Now, what is special about the standard forms, actually both Form 1 and Form 2, is it is assumed that the variables are positive, or I should say non-negative. They can be 0 too. All right. So that is a common feature for the standard forms. You won't see that in the other forms, but that doesn't mean that you can't have the constraints that the variables are positive. We can add those, but they won't be implied like they are in the standard forms. All right? And the other feature of the standard forms, one, is equality constraints. So you have some constraints, and your AI transpose, where I is AI is, for example, A2 might be a vector, and A3 is another vector. So you have M equations, and here you have an inner product. So, in fact, you can put this into a much more compact form, obviously, when you put it into matrix form. So here you have a more compact form. So let's just remind ourselves, thinking about linear algebra, how this AI transpose X equals BI will be put into AX equals B. All right? So first of all, let's define X. So X is equal to the vector X1, X2, ... Xn. So I'm assuming there are n variables, as was shown here. Okay? So when if I come down here and I say X is greater than equal to 0, this is really a 0 vector. Okay? So, X1 is greater than 0, X2 is greater than 0, so on. Now, let me define what A would be. So A, if I write it longhand, you would have A11 times X1 plus A12 X2 plus ... A1n Xn has to be less than B1. Okay? And then you'd have A21 X1 plus A22 X2 plus ... A2n Xn is less than B2. And then all the way down to AM, okay, so we have M equations, AM1 times X1 plus AM2 X2 plus ... AMN Xn is less than BM. Okay, so here we have M equations, and I think you can see that the A matrix will be A11, A12, ... A1n, and then down the line. And each row will be these coefficients in front of X. And of course, the B matrix is just equal to B1, B2, dot, 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 BM. Okay, so this is the standard form in a more, in compact form, in using linear algebra, okay? Or using matrices. All right, so there's standard form 1. Let's look at the inequality form. So it's only slightly different, okay? Well, for one thing, you no longer have equality constraints, you have inequality constraints, okay? So, and the other piece that is missing is your requirement that your variables are non-negative is no longer part of the form. So for example, in this form, the variables could be negative. That's fine. That's not the case in the standard form where they must be forced to be positive, or non-negative, I should say. So, but again, I'll show you an example where just because it's not implied, I can still add them to my constraints as equations, and you can still require that your variables are positive, and we'll see that. We'll see a nice example of that. Okay, so again, same manipulation of the equations, and actually the A matrix becomes exactly the same as we had in the last one, except we have our inequality and we don't have our non-negativity constraint. All right, so this would be A11, A12, dot, 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 A1n, and then dot, 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 AM1, AM2, and then AMN. Okay, so that would be our A matrix. And B, of course, again, same thing. You have your B1, B2, dot, 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 BM, because there are M equations, right? And your C matrix, your C vector, is C1, dot, 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 to Cn, because the C vector has to be n long to take the inner product with x. All right? So that's the only difference. Now, again, the interesting things come in when I go from different forms. So that'll be in the next short lecture. Okay. So now let's talk about standard form 2. So the only difference between standard form 2 and standard form 1 is that instead of equality constraints like we had in standard form 1, we have inequality constraints. Okay, so we have minimize C transpose X, subject to AX is less than B, and then of course the implied X is greater than 0 vector. All right, so the only difference is in the standard form 1, it was AX is equal to B. In standard form 2, it's AX is less than or equal to B. But this non-negativity of your variables is still part of the form. Okay, so depending on just by looking at it, if I say standard form, but I use either the inequality or the equality, it's still standard form. Okay, so now. We're almost done. Really, the last thing is a more general form that would include both equality constraints and inequality constraints separately. Although later, in the next, as I said, in the next video, I will show you how to combine them into either turn equality constraints into inequality or turn inequality into equality. So here you can see that we still have our cost function, and then now here we have inequality, and here we have equality, and we just separate them into two different matrices. The G would just include the equality portions, and the A will include the inequality portions. All right. As you can see, there is no explicit X is greater than 0 in this case. Okay, but again, we'll see that next. How do we would then try to plug that, if we had non-negativity constraint, we would try to put that into our A matrix. All right, so we're going to see that in more detail in the next lecture. All right? So continue to join me.